Chapter 11, Section 5. If I remember correctly, we've dealt with triangles, we've dealt with quadrilaterals. Now we deal with a more general term, which is polygons. Poly means many, and so this is things that can have multiple sides and different numbers of sides. So a polygon, by definition, is a closed figure formed by three or more line segments called sides. The segments that form a polygon intersect only at their endpoints. So essentially what they are emphasizing with this definition is I can't have something that doesn't actually finish the side. This is not a closed figure, this is an open figure because we got this opening right here. But it's also saying that we can't have it where they cross over each other like that. So we can't have this part, it has to end at that end point where they meet. We can't have things extending out beyond that. So this means they cannot have any curved lines. Their lines cannot overlap, cross over each other like I drew there. And the end of each line segment must connect to the end of another. So now we'll talk about names of polygons. You should be very familiar with triangle and quadrilateral. And the prefixes do help you know the number of sides. Tri, 3, quad, 4. And if you've not heard of it before, the Pentagon is a building near DC. And the Pentagon is a building that has 5 sides. It's one of the buildings that was attacked back in 9/11. Hexagon, hex means 6. Heptagon means 7. Octo, like octopus, means 8. Nonagon, 9. Decagon, like decade, 10. So there are names that they've made up for things more than 10. I think there's dodecagon, might be the name for 12. But we don't have to remember anything beyond that as far as this class is concerned. Anything bigger, we'll just put the number of sides, a dash, and then gon. So if it has 11 sides, we'll just call it an 11 gon. 12 sides, we'll call it a 12 gon, and so on. So the first thing you need to know how to do in this lesson is be able to look at the shape and figure out, is it a polygon? If it's yes, you should name it. If the answer is no, you should say why it's not a polygon. So for example, in number 1, we would have to say no, this is not a polygon because of the curved line. We can only use straight lines for polygons. Okay, number 2, this is a polygon, so we say yes. It follows all the rules, all the lines are straight, they all meet at their endpoints. There's no spot where they don't meet, so it hits all those marks. So we need to count how many sides we have. 1, 2, 3, 4, 5, 6. So 6 means a hexagon. So yes, number 2 is a polygon, and it is a hexagon. Give me a second. Okay. Okay, number 3. It is also a polygon. It meets all the rules. Nothing crosses over. They do all meet at their endpoints. They're all straight lines. So let's see, we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Whew, okay. So we have 12 sides, which we'll just call a 12 gon. And if you want to mark them just by putting a notch, like honestly, I think it's simpler to just say 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. It's fine to do that. I won't count off if I see you do that. I'm choosing not to do that in the notes though, because as you may remember, these notches usually mean those are all congruent sides, which isn't true here. But it can also be a good way to just mark it when you're counting the number of sides. Number 4, this is not a polygon because of this spot right here. It's an open figure. It needs to be closed. All the endpoints need to connect to another endpoint. So it's because it's an open figure that we have to say, nope, it's not a polygon. So that's the first task, is being able to look at a shape and say, is it a polygon or not? If it's not, tell me why not. If it is, name the shape. Okay. You may remember we talked about a triangle has 180 degrees, and a square, or excuse me, any quadrilateral, not just squares, any quadrilateral has 360 degrees when you add up all of its angles. So there's actually a formula right here you can use to figure out the sum of all the interior angles of any polygon. So it turns out if you take the number of sides and subtract 2 and multiply by 180, that will tell you how many degrees there are in total. So just to show you this works with ones we've already done, like a triangle has 3 sides. So 3 minus 2 times 180, 3 minus 2 is 1, 1 times 180 is 180. So that shows us a triangle has 180 degrees. Quadrilateral, we'd plug in 4. 4 minus 2 is 2. 2 times 180 is 360. So you see this rule, while we weren't using it for triangles and quadrilaterals, it does still work with those. And it works for the reason I believe I talked about in the quadrilateral section. Why does this work? It's because every polygon, no matter how they're shaped, every polygon can be split into triangles. And I think I showed you something like this right here in the quadrilateral lesson, where you could do a diagonal line or just a line from one, let's see, what's what I want, endpoint, I can't remember, I'm losing the name. One point diagonally to the other. That splits it into 2 triangles. And then you can see the pentagon. If we do a similar activity, this splits it into 3 triangles. So the number of sides is 4. As we showed up here, 4 minus 2 is 2. 2 times 180 is 360. So let me back up. I'm not filling the blanks correctly. So there are 4 sides, and there's 1, 2 triangles. And if there's 2 triangles, we do 2 times 180 and get 360 degrees. With the pentagon, there's 5 sides. There's 1, 2, 3 triangles. Well, each triangle has 180, and 3 times 180 is 540. I know they didn't ask for these degrees, but I'm just trying to illustrate how the number of triangles relates to that. And this, let's see, it's a 1, 2, 3, 4, 5, 6, 7, 8. It's an octagon, so 8 sides. And there's 1, 2, 3, 4, 5, 6 triangles. So if we did 6 times 180, is that 1080? Yeah. Get 1,080 degrees. So an octagon has a total of 1,080 degrees. And the reason we can figure that out is because an octagon can be split into 6 triangles. So let's use this formula to figure out the sum of the measures of an interior angles of a nonagon. So you need to put this formula in your head. N minus 2 times 180. N is the number of sides the shape has. A nonagon has 9 sides, so I'd plug in 9 for N. 9 minus 2 is 7. 7 times 180 is 1,260 degrees. Six, what is the measure of each interior angle of a regular nonagon? So this is important to understand what the word regular means. As far as polygons and shapes are concerned, a regular means it has equal or congruent sides and congruent angles. So I believe what I have drawn up here, this would be a regular pentagon. It looks like all the sides are equal, all the angles are equal. You need to ignore the dotted lines, just focus on the whole shape. This is also a regular octagon, has 8 congruent sides, and if you're looking at the actual angles of the octagon, not the angles of the triangle, they're all equal as well. So for a nonagon that has 9 sides, we just figured out it has a total of 1260 degrees. If it has 9 angles and all of them are equal, then we can divide their total number of degrees by 9 and find out that each individual angle inside the nonagon is 140 degrees. I think it might also help if I do a simpler one first. So let me back up just a second. Let's just think about a square. A square is a regular quadrilateral because all of its angles are congruent. They're all 90 degrees. All of its sides are congruent as well. Now we know a quadrilateral has 360 degrees in total. All 4 of those angles add up to 360. If we know it's regular, if we know all 4 of the angles are the same, we could divide the total by 4 and find out that each of them are 90 degrees. So the idea is that if it's regular, you can take the total and divide by the number of angles you have to figure out what each angle is equal to. And with the formula n minus 2 times 180, you can also figure out, based on the number of degrees, what the shape would be, or how many sides the shape has, I should say. Because one thing I didn't do that I could have done up here is say n minus 2 times 180 equals the sum of the angles. So I'll just use an S for sum. So this formula is really S equals n minus 2 times 180. So when they tell us how many sides, or they tell us the name of a shape, we can plug in for n and find the sum. But we can also plug in the sum for S and find the number of sides it has. So that's what they want us to do here. They say what polygon would have 1,980 degrees as the sum of its interior angles. So we plug in 1980. Then we divide both sides by 180. That gives us 11. So 11 equals n minus 2. Then I add 2 to both sides. So it turns out that if the sum of all the interior angles adds up to 1980, that shape must have 13 sides. So it is a 13gon that has that as its total angle measure inside. Okay, last thing for this lesson. There we go. So this is not a heavy thing you have to remember a whole lot of, but I want to introduce this idea to you. A repetitive pattern of polygons that fit together with no overlaps or holes is called a tessellation. The sum of the measures of the angles where the vertices meet in a tessellation is 360 degrees. So a very simple example of a tessellation would be like a chessboard, or it can be checkers, same thing, because you know it's all equal squares. I'm not doing the right number of squares, I'm just illustrating. But those are all squares. They all meet together. You're using the same shape everywhere. It's all squares. There's no gaps between them. They all fit together very snugly. But if you think about just kind of like zooming in on one, what they're pointing out is if you take all the angles that are right here, it's going to equal 360. Now that's true even when there's more creative shapes than just squares that meet. I'll try to pull up a picture in just a moment so you can, I'll do it now. Okay, here's some other example of tessellations. You can see where they got things fitting together. But their point is that anytime you see lines meeting, like right here, if we did these angles all together, it's going to add up to 360. Or even with these crazy arrows, they all add up to 360. even with these combos of hexagons and triangles. See that dot right there? If I was to measure all the angles all the way around that dot, it added up to 360. So that's the point that they're making. So the sum of the angles where the vertices meet. So we're not talking about all of the angles, because this goes on forever, so it has infinite. But the sum of where the vertices meet is 360. So here's the question. Can every regular polygon form a tessellation? Because actually some of the tessellations that I pulled up there on Google, they use more than one shape, which is really not what we're talking about at the moment. We're saying the same shape everywhere, not a combination of different shapes. Now, there's some cool patterns and artwork that use different shapes for sure. But we want to figure out then, can every regular polygon form a tessellation? Well, it can only do that if 360 divided by its interior angle measures ends in a whole number. So, for example, since these are all identical, they're going to be regular. So when I have a square, I know every individual angle is 90 degrees. So the reason I can know squares work without even thinking about a chessboard is if I say, all right, 360 divided by 90 is equal to 4. So since that's a whole number, I know that works just fine. Same with triangles. A triangle, I would do 360 divided by 180 and get 2. That's a whole number, so triangles would work also. Sorry, I didn't do that right. I don't do 360 divided by the total. I do 360 divided by the individual one. So a regular triangle, an equilateral triangle, would have 60 degrees in each one. So I would do 360 divided by 6 and get 6. So this is still a whole number. I was just dividing by the wrong one. So if they ask you on the homework or a quiz or a test, can this form a tessellation? You've got to figure out what will each interior angle equal, just like we did up in number 6. Then do 360 divided by that number. So let's actually go back to number 6. This would be another good check. So we know that the nonagon, the 9-sided triangle, is 140 degrees for each angle. So 360 divided by 140. Let's see if that comes out to a whole number. So 360 divided by 140. Since that did not come out to a whole number, that tells me a nonagon cannot be used to make a tessellation. I already figured out, what was that, 4.7 something? 2.57, there we go. Okay. So a nonagon cannot be a tessellation.